we are very soon going to be done with all of the derivatives of all of the functions, basically, that we can take a derivative of, which is kind of cool. And we only really have a few left to do. Now, last day, major things. We derived that the derivative of e to a function of x is e to the function of x times the chain rule factor. Very, very powerful. This is one of our favorite derivatives because it's kind of hard to mess it up. And that the derivative of the natural log of a function of x is 1 over the function, again, times the chain rule factor. These are both very, very simple to apply in general. And the only derivative you're actually taking within the problem technically here is the exponent, and here it's the argument. What if I have a base that is not e? What if I have, 10 to the x power or log base 6 of a function or something like that? How do we do that problem? Well, that's what I'm going to start with today, because that does come up, although not nearly as often. So the first question, the first one I want to look at, and my erasers are dying on me here. Going back to algebra, okay, I know that if a to the x equals b, then x equals the log base a of b. Okay, that's great. Now, think about when you were in algebra, okay? You're an algebra student, and you were asked to solve things, maybe using a logarithm. So I know if I said solve, if I said solve 2 to the x equals 8, if I said solve 2 to the x equals 16, I think all of us would have an easy time with that, okay? 2 to what power equals 8? I'm pretty sure that would be x equals 3. 2 to what power is 16? I'm pretty sure that would be x equals 4. Okay, that's it. That's an easy problem. But technically, x equals the log base 2 of 8, which is 3. Here's the log base 2 of 16, which is 4. So what if the question was 2 to the x equals, 11.6? Oh my goodness, what do I do in that case? Well, again, technically, x is a logarithm. So technically, I'll write it over here, x is the log base 2 of 11.6. Okay, great. So then I just go over to my calculator, my super TI 89 titanium, and I look for the log base 2 key. It doesn't exist. Only the 36X Pro actually has the ability, I believe, to change the base. So I want to calculate that, but most calculators don't have a base 2. Most calculators only have E and 10. And in fact, just as a general rule, how do I solve this? Because it makes perfect sense. Well, here's one thing I do know. I do know the answer really ought to be between 3 and 4. Right? Because 11.6 is between 8 and 16. So how do I do this problem in general? So now I'm going to back up to what we learned. Oh, I keep dropping my erasers. What we learned in algebra. So let me go back up to here. Now the log and the exponential functions are basically one-to-one functions. If I give you one, you can give me the other, and then back and forth. They are perfect inverses of each other, as we saw evidence from the graph. So let's go back to this statement here. If I take the natural log of both sides, that is absolutely true. If two things are equal, two positive quantities are equal, and I take the natural log of both sides, the natural log of those quantities have to be equal because of the nature of the logarithmic graph. Now, this guy here, right, comes down. Remember, abominable snowman. And now I'd have that statement. Well, the question was, what is x? So clearly, I can clearly write x at this point and say that x, which, by the way, didn't we say x equaled the log base a of b? Isn't that what x was? But looking at that statement right there, x is also then the log b over the log A. Oh, and we have a handy dandy super formula right there. That's generally referred to as the change of base formula. You say, well, I have a calculator that'll do that for me. That's really nice, but that calculator won't help you when you're doing the calculus part. So if you have a calculator like a 36X Pro, I have one of those, where you can actually do a change of base on the calculator and you don't have to know that. It won't help you if you have functions. It only helps you if you have numbers. And you're never going to be taking logs of numbers. You're going to be taking logs of functions. So this is a handy dandy formula. So going back to here, I want to do this on a cheap calculator. All I got to do is say natural log 11.6 over natural log 2. Now, when I do that on my calculator, log 11.6 over log 2, my calculator says it's approximately 3.536. All right. 3.536. I'm doing this partly to introduce a symbol that you should all be familiar with, but you might not have used. This is the symbol for approximation, equal with a dot. And I see people use every symbol under the sun, including things they just made up on the spot. There's only one symbol that has ever meant decimal approximation. It's that one. It's not in the older textbooks because calculators didn't exist when the older textbooks were written, so there was no way to actually do the calculations. Squiggle has nothing to do with a mathematical calculation. Squiggle means asymptotic, okay? You would never use the squiggly. Squiggly means nothing when it compared to a number. That's different context, different ballpark. I don't care that your other instructors used it. They were using the symbol incorrectly. This means asymptotic. It has absolutely nothing to do with numbers. Now, you can use it with numbers because asymptotic would be equivalent to saying I'm estimating. We're not estimating, we're calculating. This is an infinite non-repeating decimal sequence. I can't write the whole thing, so I'm going to round it off. That's what that symbol means. You calculated it accurately, but you rounded it off somewhere. So now that's great for calculating numbers, but how's that going to help us with functions? Well, it turns out I'm going to use the same formula to some degree. So here's my goal. All right. Y equals a to the x, where a is a constant, right? A is great. A is a legitimate base. A is 2. A is 10. A is 100. A technically could be e, but let's assume a is any base really other than e. And I want to find dy dx. I want to find the derivative of 2 to the x or 10 to the x or anything else to the x power. How am I going to do that? Well, I'm going to use facts that I now know because of the logarithms. Okay, so let me erase some of this stuff. Now, how do I mess with this? Well, here's a really, really cool log and exponential property. If f of x is positive, then f of x is equal to e to the log of f of x. That's an absolute. The reason f of x has to be positive is because I'm taking the log of f of x. And if f of x is not positive, then I'd get imaginary numbers, and we don't want to go there. So my function is positive. This is an identity. Remember, e and the log are inverse functions. They would undo each other. So just as a general rule, if I said, what is e to the log of 6? It's 6. There's nothing clever going on there. So that means I can rewrite this as e to the log of a to the x. Okay. Now, can I do anything with that exponent? Oh, yes, I can. Again, it always makes the noise. Okay. This is where abominable snowmen are really, really helpful because they like, except this guy's not going to bounce out of the problem. So this is now e to the x log a. Now, how do I read that? Well, that's a coefficient. That's just a number. If I ask you to differentiate, just to remind you, if I said differentiate e to the 3x, wouldn't you tell me it's e to the 3x times 3? Because 3 would be the chain rule factor. It would be the derivative of 3x. If that's not just an x, then I have a chain rule factor. Well, log a is just a constant, right? Log 2, log 10, log whatever. Oh, so dy dx, which is of course the derivative of e to the x log a, is e to the x log a times log a. Log a is my chain rule factor. It's the constant. So if that was, log 7, then this would be times log 7. No big deal. Now what? Well, didn't e to the x log a come from a to the x? A to the x and e to the x log a we just showed. These are exactly the same things. I cannot differentiate this one, but I can differentiate this one. That's why we rewrote it. But now I want to go back. So that is just a to the x. So the answer is a to the x log a. Oh, so now we have a formula. If y equals a to the x, its derivative is a to the x, that sounds familiar, times that additional term. Okay, that makes sense. So I know the derivative of e to the x is e to the x. So if I use any other base, the derivative of any other base to the x is the same thing, that base to the x, but multiplied by this additional term. That came from the chain rule factor. Now, what if a turns out to be e? Well, the natural log of e is 1, right? So we just get back to our original formula. That's a good thing. So now, what if, since I've got that one, what if now I want to do the general, I want to now find the derivative of a to the u of it. I want to be able to do any base that's legal to any function of x power. That derivative would be, of course, a to the u log a. And at some point, I got to take that derivative. So then times the chain rule factor. And this is the grand formula that we've now derived. I can now differentiate any base. We already knew how to do e to the u. The derivative of e to the u last day was e to the u times the chain rule factor. So now we have any base to the u, which is practical. Now, most of the time you're going to be dealing with bases of e, but what if you're not? In a chemistry situation, you typically don't use bases of e. In chemistry, you're usually using bases of 10, but you still might have derivatives. So derivatives in chemistry, remember, a derivative is an instantaneous rate of change. And there are rates of change in chemistry. So let's do a couple of examples. Let's keep it simple. I want to start with, let's differentiate, let's keep it simple, 10 to the x. Well, according to that formula, it's 10 to the x. But times the natural log of 10. That's it. It's actually that simple. All right. What if I wanted to do, how about 5 to the cosine of x? All right, let's make it more exciting. Well, I'm going to start by writing 5 to the cosine of x. Okay. I still have the log term, so I still got to have the log of 5. And I've never actually dealt with the cosine. Oh, that's my chain rule factor. I need the derivative of the cosine, which would be the negative of the sine function. Okay. Now, everything I've said is true and correct. Question is, how should I represent that final answer? I got 3 things going on here. Now, by the way, there is no absolute rule. There is no rule for how you have to represent your final answer. But a good starting point is log 5 is a scalar. It's a coefficient. So it really shouldn't go in the middle. It really should go in front. And I also have a negative sign. So I'd probably write negative log 5. Now what? Well, I've got a sine function and a 5 to a power. So I would probably do something like this. Times the sine of x times 5 to the cos x. By putting parentheses here, I'm not somehow accidentally including the sine function with the log, and I'm not including anything here with the 5. The order is not critical between these two, but I think this may be the easiest to read in that form right there. And calculus students are notorious for not liking to use parentheses. We do goofy things. We do goofy product rules. But parentheses in this case are really, really helpful because when you're doing a logarithm of what follows it, if I wrote, for example, this is important, if I wrote log 5 times sine x, it's kind of ambiguous. Is it 5 sine and then I'm taking the log, or am I taking the log of 5 and multiplying the results by the sine? The lack of parentheses can make it a little bit ambiguous. And this, I want to get into this because I'm seeing a lot of this when people are doing problems where parentheses are absolutely required. Like you're using a quotient rule and you're taking the derivative of an entire quantity. People don't use parentheses, but then it's causing wrong answers because we're misreading our intent by not putting the parentheses. I'll give you an example. If I said, keep it simple, the cosine xy, as a general rule, is that the cosine of x multiplied by y, or is that the cosine of the product of x and y? Or is the correct answer, I can't tell. By the way, almost all textbooks that I've seen, when xy is the argument, they won't put parentheses. They're notorious for not putting parentheses, but this has two possible interpretations. This is either cosine of x times y, or it's cosine of the product of x and y. By the way, these are not remotely similar. There's nothing about that. They're as different as you could possibly be. But the problem is, if I write this and you're not sure which one I meant, then we have a serious problem here. So if my argument is xy, absolutely it's required to have parentheses. I mean, this is just simple arithmetic, order of operations. Oh, if I don't write parentheses and I entered this on my calculator, the calculator is going to do this, because the function precedes multiplication. But if I actually wanted this, there's a really simple thing I can do. If I actually wanted this, then I should have just written it like this. Then there's no way it could be misinterpreted. So the problem with not putting parentheses when there's the potential for ambiguity means that somebody may misread the intent. So I'll give you another simple example. I have the derivative of f of x and g of x. And I know that's the derivative of f of x times g of x plus the derivative of g of x times f of x. Now I'm having fun with this one because about a third of the people write this for the product rule. You do realize that I just wrote the same thing essentially 3 times. This is absolutely incorrect, by the way. This is as wrong could be. Yet I find that a significant number of calculus students, this is their version of the product rule. No, the fact that I didn't put parentheses on anything to the right means I'm differentiating that product. And then I'm saying it's equal to the derivative of the exact same product, equal to the derivative of the exact same product in reverse order. And since nobody ever actually thinks to do this, first of all, this is an operator. So technically, I have to have parentheses around the whole thing. It's an operator. Secondly, I only wanted to differentiate the first one. So I need parentheses here and here. I've never seen a human being actually do that. And here I need parentheses here and here. Since nobody ever does that, this one absolutely is critical. You never put the derivative in front of the other function because you would have to use 2 sets of parentheses. No, that's not what the product rule is. Product rule is first times the derivative of the second. It's not the derivative of the first times the second, but its commutativity doesn't matter. No, it does matter because you absolutely would need 2 sets of parentheses. Sorry, without the second set of parentheses, you're still differentiating the entire product. So you just wrote the product rule equals itself plus itself. And by the way, you still haven't taken a derivative yet. So the lack of parentheses can get us in big trouble. Err on the side of putting too many in them. Now, we have just figured out a way to differentiate any base raised to a functional power. That's pretty powerful. So now let's switch gears a little bit. What if I wanted to differentiate a logarithm of a different base? In other words, let's suppose my y is the log base a of x, a being any legal base, but suppose it's not e. So it's not the natural log of x, it's the log base 3 of x, log base 12 of x, some other base. And I want to find dy dx. Now this one here is far less common than the previous one. The previous one, differentiating, 10 to a power, that's actually not that uncommon. E is still way more common, but differentiating a base that isn't the natural log is actually very uncommon. You would run into this. But again, like I said, in chemistry, you use log base 10 all the time. You don't use log base E. So you may actually have a rated change with a different base. So how do I do that? Well, we do have that change of base thing. Excuse me. Now, going back to the change of base, just to remind you, log base A of B, we just figured out a moment ago, is this. This is what I derived a few minutes ago. Hopefully you've done this in algebra and pre-calculus. So how do you remember the change of base? Well, it's actually pretty easy. This B is higher than this A, and so therefore it shows up. That's a really easy way to remember it, okay? So I want to differentiate this. All right, how do I do it? Well, first thing is, can I write this as a quotient of natural logs? Yes, I can. According to the change of base, wouldn't that be log x over log A? It's the same formula. Okay, so this is equal to this, period. But isn't log A just a number? It's just a coefficient. So I could actually think of it like this. This is 1 over log A times log x. This is just a constant. Oh, so then wouldn't the derivative be constant times the derivative of log x? Yep, and that's my answer. So if I'm differentiating a constant times a function, it's just the constant times the derivative. Okay, so now I've got a nice simple formula. If this base is not E, then the derivative looks like this. And by the way, I can make this into one quotient easily enough, or I could leave it like this for now. I'm going to leave it like that for now. Some textbooks will write this, by the way. Some textbooks will write it like this. That's exactly the same thing. There's no difference. I'm gonna leave it like this for right now, just for practicality's sake. So if I'm differentiating a base other than E, I get the additional term that has a log. Oh, that's familiar. When we differentiated, 10 to a power, we multiplied by the log A. Now when I'm differentiating a log of a different base, it's 1 over log A that shows up in the answer. Interesting. The exponential is times log A. The logarithmic, it's 1 over. Remember, those are inverse functions, so that's not a great shock. Now let's go one step further. What if I'm now doing a function? I now want to differentiate the log base A of some function of x. Remember, u is a function of x. So it should still have that form. What is this? So it's still going to be 1 over log A, 1 over u. But now I take the derivative of u. Okay, that's it. Now this one, like I said, is a little more obscure. Let's do an example or two. I want to take the derivative of, how about the log base 9 of x? Let's start with an easy one. Well, I just apply that. This will be 1 over log 9 times 1 over x. And I can make that into one quotient. In fact, I probably should. I want to differentiate the log base 2 of the secant of x. Okay. Well, we'll start the same way. 1 over log 2 times 1 over secant x. That's a good start. At some point, I need to differentiate the secant of x. So times the secant x tan x. Well, now what? Well, clearly, you cancel those guys. Now, this is a coefficient, so it really should be in front of. And that's the best answer I can give. Should I put the tangent in the numerator? No, you're going backwards. You have a coefficient, you don't make it into a quotient because that's not a quotient. This is just a number times tangent. This is, if I thought of it as a hideous decimal times tangent. Okay, so that ends that discussion. That wasn't too bad. Now, there is one truly evil problem. Oh, and it is so much fun because it is just so diabolical and evil. We're going to do a derivative that doesn't actually have a formula, but it's a technique. So implicit differentiation isn't a formula, it's a technique. I differentiate both sides, gather terms, and I report an answer. What I do is I differentiate the individual terms with their derivative formulas, but there's no such thing as a formula for implicit because there's an infinite number of variations of the question. So here's what I'd like to do. I would like to find the derivative. And by the way, there's a reason for this. When we get into the graphing and other things, it'll be really, really clear, and also limits. But consider y equals x to the x power. Now that just feels wrong. I know what to do if it's x to a constant. And now I know what to do when it's a constant to the x. But what if it's x to the x? I want to find dy dx. Well, would it be x to the, do I bring this down and decrease the exponent by 1? No, I only do that when it's a constant. Oh, then do I say it's log x? No, I only do that when that's a constant. No, there is no formula we've ever learned that I can apply because we know x to the n, we know a to the x, where that's a constant, where that's a constant. Okay, neither one of those apply because that's not the case. So how am I supposed to do this? Well, one way to do this is by using that trick that we did a while ago. By the way, just so you know, the domain for this has to be positive numbers. The x's cannot be negative, and it can't be 0. 0 to the 0th power is a particular type of indeterminate form that, in fact, my Calc 2 class will be working on tomorrow for the first time. They're going to actually explore some of the more difficult indeterminate forms. But the domain must be positive numbers, otherwise my output will all be imaginary. But I can do this. I can say x to the x is equal to e to the log x to the x. That I can say. And if I do that, let's do it. This is why we love logarithms. Well, I love logarithms. You may not love them yet. So for every positive number, for every positive real number x, this is equal to this. But if I told you to take the derivative of this, that doesn't look that scary. That doesn't look scary at all. X log x, that's not complicated. So dy dx, which of course would be the derivative of e to the x log x, is just e to the x log x. Oh, okay. Wait a minute, there's another chain rule or something? Times the derivative of this. Okay. Whatever I get here is my answer, but ultimately that's just a simple product rule. That piece right there is just not complicated. I still have to differentiate. So right now I've got e to the x log x times what? First times derivative of second plus second times derivative of first. Okay, well, I like that one. So this is e to the x log x times what? 1 plus log x. All right, so there's my answer. There's my derivative, except the problem started with this, and this looks really, really busy. You do notice something, I hope. Isn't this that's just x log x. I rewrote x log x in this form so I could differentiate it. So now I'm just going to simply put it back. This is x log x. So the answer is, I'm sorry, x to the x power, sorry. The answer is x to the x. Oh, cool. So this function that doesn't have a formula for its derivative, we used a technique and we got it. And so basically it comes down to what if. So it's a what if. So here's what we're looking at. What if y is function to a function power? Okay, that's the ultimate evil you could ever deal with in calculus. I have a function and it's raised to a functional power. I know what to do when it's a product of functions. That's easy, product rule. Quotient of functions, quotient rule, piece of cake. Sum of functions, sum of derivatives. Nothing challenging. But I have a function raised to a functional power. So as long as, right, as long as this guy is positive, this is e to the log of f of x raised to the g of x. And then what would I do? I'd take this, and then I would do this problem. So this is the technique. It's not a formula because your final answer is going to be different for every single thing you get. This is sort of the ultimate challenge because we're doing logs and exponentials, and there's a product rule in there. But we can now differentiate anything logish or exponential. There's no rules now that say, no, you can't do this one, but you can do this one. We can do everything. All right. So with that, I'm going to show you another little tool that makes logarithms particularly useful. Now, in a business calculus class, the most important type of function they actually deal with are logarithmic functions, strangely enough, because of the nature of them and the things you can do. If you think about it, the derivative of a logarithm, remember, is 1 over the function times derivative of function. So in general, would it be legal to write it like this? Just give me a yes or no, yell it out. Is that legal to write that? Anybody? Is that legal? What I just wrote?
Should we have a log there, or but? I mean, I want to.
This is either absolutely true for all functions that exist, or it's not. It's an absolute black and white. There's no gray area. Is that true or is that not true? Yes or no?
Yeah.
Yes, this is absolutely always true. There's no exception. There's no time. What do? I did 1 over the function times derivative of function. So why did I write it that way? This is called, marginal. If you've ever heard the term, if you've ever had an economics class, for example, you talk about marginal profit or marginal revenue or marginal costs. Has anybody ever heard that term before? Marginal something?
Utility.
Marginal utility. The term marginal means the ratio of the derivative over the function. That's the only time it's ever used in that context. Oh, I can't get marginal unless I'm differentiating a logarithm. Now I can create this ratio, but so if I said this is the marginal f of x, so let's say f was my profit function, then this is called marginal profit. Interesting. Now I'm not an economist. I've had economics, but this is something that's extremely important. And the only way you can get that is to actually use a logarithm. Okay, my f of x isn't a log, but if I take the log of f of x and then differentiate it, I get my result that I want. So sometimes it's necessary to take something that has nothing to do with an exponential or a log, but make it into a logarithmic problem, which sounds kind of backward at first, except we're going to see all the tools. So we're going to go over something called logarithmic differentiation as opposed to the derivative of a logarithm. Logarithmic differentiation is the idea that if I start with something and I change it into a log problem, it might make my life easier. For example, if y equals f of x, let's assume there's no logs whatsoever in that statement. If y equals f of x and this is greater than 0, then the natural log of y equals the natural log of f of x. Again, it has to be greater than 0, otherwise I'd be taking logs of negative numbers. Okay. Now, if I differentiate both sides, Remember, y is a function of x. So what would the derivative here be? It'd be 1 over y times dy dx. On the other side, what would I get? Well, we just did it a moment ago, didn't we just say we'd get f prime of x over f of x? Okay, if I multiply both sides by y, now I've got dy dx equals y times f prime of x over f of x. But since y equals f of x, those cancel, and I have dy dx equals f prime of x, which, by the way, is a good result because it means that everything I did was valid. But wouldn't it have been a whole lot easier just to start by saying dy dx is f prime? It depends how complicated the function is. There are certain functions that are just complicated enough that I don't want to differentiate it as it was stated. I might find this to actually be easier. We're going to do a few examples of this. This turns out to be an extremely powerful tool. Now, it does feel like circular reasoning. That's true. Dy dx equals f prime of x. Well, I already knew that. But I got the same result by doing this logarithmic differentiation. I did that to prove to you the validity. If I have a statement like this and I take the log of both sides and then differentiate, I will always still get my final result correctly. Okay, so let's do an example. I'll do some really simple examples. Then we'll do some complicated ones and you'll see the benefit, hopefully. All right, let's start with something really simple. Y equals 10 to the sine x. Okay. If I differentiate both sides, I already know what the answer on the right is. I already know the answer is going to be 10 to the sine x log 10 cos x. But let's just for fun, because that is our primary goal here, let's take the natural log of both sides. Can I then write this as sine x times log 10? Yes, I can. That's why I would do that. Now, what do I have on the left? If I differentiate with respect to x, I'm going to have 1 over y times dy dx. On the right, I'm going to have cosine of x times log 10. Several of you want to do product rule in the worst way. That's not a product. Log 10 is a coefficient. You never use product rule on a coefficient because it's not a product of functions. Product of functions is two different things with x's in them, right? If I said I have 6x, the derivative is 6. You don't do a product rule. But if I had 6x times cosine, now I have a product of functions. I'd have to do both. So right now I'm almost done. What is dy dx? It's y times the cosine of x times the log 10. So I substitute that back in. And that's the answer we already knew we were supposed to get at the beginning. It would have been a lot more efficient for you to just take the derivative of both sides. Yes, I agree. I don't use logarithmic differentiation on this, although when I do have something in an exponential form like that, logarithmic differentiation can sometimes make things easier. No, I'm going to show you where you really want to use logarithmic differentiation. Okay, where this will really be a time saver. In general, let's suppose y equals f of x times g of x. And I know if I differentiate both sides, right, that's straight up product rule. That's a piece of cake. That's not even a question. Times h of x. Times p of x. All right, just having fun. What if I have more than two functions in a product? How do I do product rule on that one? Well, let's just say I had 4 functions here. Well, there's no absolute rule. There is one answer I can get. There's only one correct answer. Now, you might say, well, if they're all polynomials, then I'll just go ahead and multiply the whole thing out. Well, that might take me a week. Okay, I don't want to do that. I could look at it like this. So think of this as my first function. Think of this as the second. So first times derivative of second, but within derivative of second, I would perform the entire product rule. Plus second times derivative of first, and then I'd do the whole product rule. That's a really clever way of attacking that one. But you realize, we're going to fill up this board a couple times. It's absolutely correct. But man, that would be a long problem. Boy, what if I said, let's take the log of both sides. Why would I do such a thing? How does that make it easier on me? Don't I still have the hideous product rule? Not anymore. Don't we know that the log base A of the product is the log base A of the first plus the log base A of the second? Isn't that a log property we know? That the sum of the logs is the log of the product? We know that the difference of the logs is the log of the quotient. I've got a log of a product. That means this is equal to the log of f of x plus the log of g of x plus the log of h of x plus the log of p of x. Oh, I don't know about you guys, but I think each of these individual derivatives are going to be really, really easy. I don't care what the functions are. This is way simpler. So now what is dy dx? I'll write it this way. How about f prime over f plus g prime over g plus h prime over h plus p prime over p. Big yikes. Sorry, almost forgot. 1 over y, sorry, 1 over y dy dx. We're not done yet. Now, let's assume that maybe these were polynomials, maybe there were trig functions. It doesn't really matter. I don't want an answer that's the sum of 4 things here. In all likelihood, I probably would want to put these over a common denominator. That's fine. You don't need to, not yet. Okay, I would now do the next step. What is dy dx? It's y times, I'm gonna put this thing times y. But what was y? F times g times h times p. Oh, when I multiply this by this, that will take care of the common denominator for me. In other words, don't bother with the common denominator if you don't need to. It's correct. But I could also just look at it this way. So what's this going to be? It's going to be, if you want f prime times g times h times p plus g prime times f times h times p, keep going, plus h prime times f times g times p, and then finally plus p prime times f times g. I didn't say the process is short, but I guarantee you, I don't care what the question is, this route will be a fraction of the work. It will be so much less work in the long run. We'll do an example, but I have a product of more than 2 things. Yes, I can still use regular product rule, but from a bookkeeping standpoint, it might be a little bit difficult. I might not actually do it correctly. I might, get lost in the process. But if I have a product of more than 2 things and I do logarithm differentiation, then I'm differentiating a sum, which is much, much, much simpler. Okay, wait, that's not even close. So let's do an example. In fact, let's do something like this. Y equals, how about the square root of 6x squared minus 4x over 2x plus 3 to the 4th power. I want to find dy dx. Well, clearly this is a quotient rule problem, or is it? I wouldn't use quotient rule on this one, not at all. We did a problem like this when we first learned quotient rule and chain rule and such. And I said, no, the easiest thing to do is rewrite this in this form. Now I would definitely use product rule. Remember, if your denominator is something raised to a power and you write it as a product with a negative exponent, this will be shorter than quotient rule 100% of the time. But I'd like to do this using logarithmic differentiation. So the first thing I really needed to do was rewrite it in this form. So the log of y will be the log of, and I do need parentheses to indicate, what I'm actually doing the log of. I'm doing the log of the whole thing. Lack of parentheses would mean I'm only taking the log of the first one. Okay. Now I know the log property says the log of a product is the sum of the logs. But what about those exponents? Oh, come on, by now. I love the sound they make when they hit. Okay, we haven't done any calculus yet, by the way. I'm only rewriting the problem, lest we forget. So I'm now at 1/2 that minus 4 log that. Okay. This is scary. This is scary for me. I know, when I look at that, okay, I'm gonna have to roll up my sleeves, make sure I'm, heavily caffeinated, and it's going to be a little while. I'll see you when I'm done. I'm going to lock myself away. This is not short, sweet, and trivial. The first thing I would do is write it like that. I do my product rule. I do all my gathering, my factoring, all that kind of stuff. But if I said, let's take the log of both sides, then the log of y actually reduces all the way to this. That derivative and that derivative are utterly trivial. There's nothing there that's scary anymore. So when I differentiate the left side, I'm going to get 1/y times dy dx. My final answer is going to be dy dx equals, which means at some point I'm going to multiply both sides by that y. But right here, what do I have? This is going to be 1/2. I'm going to be lazy and write it like this. What's the derivative of that quantity? It's 12x minus 4. And again, I'm going to multiply that by 1/2 at some point. Minus 4 times the derivative of that is just 2. Okay, so at this point in the game, I've got 6x minus 2 over 6x squared minus 4x minus 8 over 2x plus 3. Now, to put these over a common denominator would probably be wise because it would make the next step less work. Or when I multiply both sides by this, then I have to do my factoring. I think at this point, putting them over a common denominator will be a time saver if I do it now. So common denominator here means, we're out of room soon, I'm going to have 6x minus 2 times 2x plus 3 minus 8 times 6x squared minus 4x all over 6x squared minus 4x times 2x plus 3. So hopefully we don't totally mess this up. I say we're all in this together. Okay. Well, let's see. I'm going to be lazy. I'm just going to write right over the top. Hopefully you can see this. So 12x squared plus 18x minus 4x minus 6 minus 48x squared plus 32x. And I did that because I don't have enough room to rewrite it one more time. So let's see. I have a 12x squared. I have a negative 48x squared. So that's negative 36x squared. 18x minus 4x, that's 14x. Plus 32x, that'd be plus 46x. And hopefully I don't have any errors here. Errors suck, basically, All right, and then finally I have the one constant. Okay, now we can always check to see if this is factorable. I don't believe it will be. So now 1/y dy dx equals this. All right, let's see. I'm going to go ahead, since this was all of our scratch work, I'm going to erase this part right here. So I can continue. Now, what is dy dx? And if you notice so far, the only calculus we performed in the problem was this step here. This is the only calculus. Now we put them together. Yeah, in factor, we just put them together. That's the only algebra. The next thing I write, I'd really like to be the final answer if possible. So this is going to be this multiplied by this. Now stare at that for a moment. Well, I'm going to write the numerator first. Okay, when I multiply this times this, notice what I'm going to get. This is to the 1/2 power. This is to the 1. 1/2 minus 1 is -1/2. That means that the exponent will go in the denominator. Again, 1/2 power, this is on the bottom, so that means I'm going to end up with a root on the bottom. That doesn't really surprise us. -4 power, I have another one on the bottom, that would make it -5 power. Now what? We're done. That's the answer. Now, I could side by side write this next to this, that would be okay. But either way, that this guy on top, this guy on bottom means that guy's on the bottom. That's already 4 powers on the bottom. There's another power on the bottom, so that's 5 powers on the bottom. Now, had I done the traditional quotient rule, I'd probably still be writing. If I'd done this as a product rule, I'd probably done it. There were similar numbers of steps. The point being, I'm showing you an alternate way to do a derivative problem that didn't involve in any way logarithmic functions, but I made it a logarithmic problem so I could use this right here. Okay, but not only that, because my original stuff with exponents and quotients was kind of scary, it became something really simple. Okay, it became simple. Now I'm going to show you one more use of this. It's really, really cool. I first saw this way back in college. You know, in the calculus we had when I was in school weren't quite as good as the ones you have today. And factorials. Now think of a factorial for a moment. What is a factorial? If I said 5 factorial, what does that mean to you? That's 5, 4, 3, 2, 1. Okay. What if I said 69 factorial? Well, on my calculator, 69 factorial, it says it's on the order of 10 to the 98th power. So this is where I would use a squiggle. Why? Because I'm going to only write a couple of digits. This is an estimation. This is not an equal. This is not an approximation. This is an integer that I don't have access to all the digits. So I'm just going to write 1.71 times 10 to the 98th power. That's a really big number. That is huge, right? Now, if I said 70 factorial, well, 70 factorial is exactly 70 times 69 factorial. So it would be 70 times that number, which is approximately 1.2 times 10 to the 100th, if I actually multiplied it out. If I took 70 times this number, that's about what I'd see. Problem is, none of your calculators will show this. Your calculators will all say error. Wait, why would it say error if I ask it to do 70 factorial? Because most calculators won't go past 10 to the 99th power. Now my titanium, I can do 499 or 449 factorial because my calculator will go up to the 999th power. But that means I can only go up to 449 factorial. 449 on the grand scale of things is not a very big number. What if you wanted to do 1,000 factorial, 1,000,000 factorial, a bazillion factorial? The concept makes sense. The ability to calculate. What if I use the supercomputer UCSD? I've heard they can go up to 1,000 factorial. Yeah, 1,000 when I'm on the order of trying to get infinitely large is kind of, it's worthless. Our technology is utterly worthless for doing something as simple as a factorial, unless I consider logarithms. What if Okay, so let me write, what is n factorial? N factorial is n minus 1, n minus 2, 3, 2, 1. So a factorial, I start with 1. 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3, 2, 1, and so on. So assume that n is large. So I could, if I have a really old-fashioned calculator and I said 10 factorial, I could just go 10 times 9 times 8 times 7. You know, it's very long-winded. If I have a factorial key, way simpler. But if I wanted to do something large, I'm still in trouble. How about if I asked you to do the natural log of n factorial? Well, wouldn't that be the natural log then of this product? Oops, sorry. 3, 2, 1. All right. But wouldn't that be the log of n plus the log of n minus 1 plus all the way down to the log of 3 plus the log of 2 plus the log of 1, which, by the way, that's 0. Wouldn't this be a true statement? Yeah. So let's just say this equals some number. Let's just say it's the number, what do we want to call it? Let's say this is c. This is some constant. I wanted you to do, let's say 10 factorial. So if you do log 10 plus log 9 plus log 8 plus log 7 all the way down, you're going to get a number on your calculator, some hideous decimal. Let's just call that number c. So if the log of n factorial equals c, doesn't that mean that n factorial would be e to the c? Whatever this adds up to, this would be true. Okay? This is how you calculate large factorials. It's actually this simple. What if I wanted to do, you know, 1,000,000 factorial? Well, I certainly am not going to do it by hand. I would take a computer and write a simple do loop. Now, anybody who's had programming here, day one, for I equal 1 to n do, right? A do loop for a computer program is like the most simple command there is. So you would write a do loop and have the computer add up log of 100 plus log of 99 plus log of 98, you know, do it for you. It would take the computer, you know, seconds to do that for you. Now you have some ugly decimal, and my answer is this. So if I wanted 1,000,000 factorial, I do log of 1,000,000 plus log of 1,000,000 minus 1 all the way down to log of 1. I'd add those up, some hideous decimal, and then 1,000,000 factorial would be e raised to that power. It's really cool. And I can actually represent a large factorial. Okay, pretty cool. So, and by the way, well, don't have to worry about the logs getting big. No, logs don't get big. If I said do the million, the log of 1,000,000, how big is a log of 1,000,000? 1, 2, 3, 4, 5, 6. The log of 1,000,000 is around 13.8. In other words, when you take the log of the number, it becomes really small. So no matter how big a factorial you took, when you change it to logs, no, it would never be a very big number. But when you went e to that power, okay, that thing would be a big number. So this is just a really cool, it's kind of a side use. We're not going to do this in this class. In really upper level stuff, they would do stuff like this. And it's neat. All right, so we're done with exponentials and logs. Now what we want to do is start into the realm of the inverse trig. And it turns out inverse trig is very important in the big picture. It does come up a lot. Okay, so let's remind ourselves of some of the rules. So the question, okay, sometimes we forget the rules. So I want to remind you. If I said sine of pi over 6, that equals a half. We all agree with that, hopefully. Hopefully we all agree with that. So on my unit circle, all right, there's pi over 6. And that would be the point on my unit circle, root 3 over 2, comma 1/2. All right, the cosine of pi over 6, we know is root 3 over 2. Piece of cake. So now the question is, solve sine x equals a half. Okay, solve the sine of x equals a half. Well, duh, x is pi over 6, right? Well, yeah, but What I'm showing you is what's called a coterminal angle. If I start here and I go one complete revolution around, add 2 pi to the angle, aren't I at the exact same place? Oh, so if I did this over and over again, I kept adding multiples of 2 pi. What if I went backwards and subtracted multiples of 2 pi? I'm going to end up at the same place, which means there's an infinite number of representations of this place right here. See, this is pi over 6, but it's also pi over 6 plus 2 pi. Is pi over 6 plus any multiple of 2 pi. So x would be pi over 6, and the way we usually say it is times plus k times 2 pi, where k is any integer, positive or negative. Oh, and by the way, while we're at it, 5 pi over 6? Isn't the sine of 5 pi over 6 also 1/2? Oh my gosh. So I'd have 5. So I not only have 2 different positions on my unit circle that produce a sine value of 1/2, there's an infinite number of representations of each one. Yikes. Okay, this is why inverse trig functions are created, because I really want an answer that just gives me the 1/2, or excuse me, that just gives me the pi over 6. Now, how do I do that? Well, I'm going to go backwards a little bit. Okay, hopefully we all remember this. Hopefully we all remember this. So in general, okay, let's consider something as simple as a parabola. Let's consider y equals x squared. Okay, what is the domain? The domain of this is all real numbers. We know that. What is the range? Well, 0 on up. So the range would be this. We know that. Now remember, the inverse, whenever you're asking for the inverse of something, you're essentially saying, I'm going to swap the roles of x and y. Input becomes output, output becomes input, so on. So the inverse would be x equal y squared. I'm just swapping the role of x and y. But the graph of x equal y squared basically is a sideways opening parabola. Remember, if I take the line y equal x and I flip my graph over the line y equal x, that's always how you get the inverse function. And they do intersect at 1, 1. Great. Now, we know this is not a function. It's an equation. It still has a domain and a range, but it is definitely not a function, right? I failed that vertical line test. So over here, if I asked you what's the domain, you'd say, well, it's 0 to infinity. What's the range? That'd be negative infinity to infinity. No surprise, domain and range just simply swapped places. That's it. It's not that interesting. It's not that exciting. Okay, great. So if I give you input, you give me the output. That's great. The problem is, if I give you output, you're not going to get a unique input. So if I input the number 3, I'm going to get back the number 9. I know that. I'm only going to get one value. When I said the sine of pi over 6, you got 1/2. You only got one value. But when I work backwards, if I said, all right, I'm going to give you the number 9, where did it come from? Oh, if I give you the number 9, where does it come from? Aren't there 2 different x values? So it'd be like going over to here. Let me give you the x value of 9. Aren't there 2 different y values that I would get? Yeah. I only want 1 though. How do I make it so I only get 1? Well, this is where an inverse comes in. Graphically speaking, this is x equal y squared. But in terms of y and x, isn't this the square root graph? This piece? And isn't this the negative of the square root graph? You see, we couldn't solve for y because then it would be a plus or minus. But I know this. What if I want an inverse that is also a function? Then going back to my original problem, we have to do something called restricting the domain, which hopefully you did a lot of in your pre-calc class. Some of you go, oh, I don't know if I did, but you did some, I hope. If I restrict the domain of my original function, now what would I restrict it to? Well, what makes something fail to be a function? When it sort of doubles back on itself. When one input gives me multiple outputs. And a lot of you say, vertical line test. That's the easiest way to think about it. If I can draw a vertical line that passes through more than one point, it's not a function. But y equals x squared is a function, but think horizontal line now. Oh, I can draw a horizontal line that passes through 2. That's why when I flipped it, the whole vertical. If you can draw a horizontal line that passes through more than one, then we'd say our original function is not 1-to-1. So in case we forgot what 1-to-1 means, I'm going to erase this for a moment. If I take a function that is always going uphill or always going downhill. Okay, I have a terrible picture. I have a function that is always going uphill or always going downhill. We say the function is monotonic. That literally translates as one direction. Mono, of course, one. If I have a function that is always uphill or always downhill, we say it's one direction. In other words, it didn't go up and turn around. A parabola is not monotonic. It's going in 2 directions, right? It's going downhill for part of it. It's going uphill for part of it. I have to be always going uphill or always going downhill to be monotonic. If I take the inverse of a monotonic function, in other words, if I flip it over the line y equals x, its inverse will still be monotonic, meaning its inverse will be a function. Only monotonic functions have inverses that are also functions. Another way of thinking about that is we use the word 1-to-1. 1-to-1 in monotonic, the same thing. A lot of you are familiar. Oh, 1-to-1. Okay. A function that's always going uphill or always going downhill is 1-to-1. Looking at my parabola, how can I make it so that it is a 1-to-1 function? I can, if I only take one of these pieces. So let's take the positive one. If I only consider this portion of the parabola, then what is its inverse? Its inverse would be only this portion of the parabola. And this portion of the parabola would make that piece a function. Oh, so the inverse that I want would actually be the square root function, but I can only do that if I restricted the domain to this. Because then what would that do over here? It would restrict the range to only the top half. So this trick, that's what the square root is. It's defined to be the inverse of y equals x squared with a restricted domain. That way I can actually get something that's a function. So going back to our sine wave, or our sine function, sorry. How do I do that? Well, let's think of what the graph of a sine wave actually looks like. So if I said, let's graph the sine, we know it looks something like this, right? It goes on forever and ever and ever and ever. Clearly, this is not monotonic. I'm going up and down all over the place. But for me to define an inverse that's a function, right? I don't want to get back an infinite number of angles when I ask the question. I just want to get back one. How do I make it so this is a function? Well, right now, I know that the domain of the sine function is all real numbers. And the range is -1 to 1. I want to take the smallest portion of this sine wave that preserves the range, but is 1 to 1. So the easiest way to think about it, just go peak to peak. There's an infinite number of intervals I could choose, but if I go peak to peak, then I will have swept out all possible y values while maintaining 1 to 1. So the most logical peak to peak is probably this one because it passes through the origin. It's convenient. So if I restrict the domain of the sine function, so y equals sine of x, and I make the domain only -pi/2 to pi/2, you notice that's a bracket, it's hard to tell. And I know the range is -1 to 1. If I take that portion only, then I can define an inverse. Now remember, inverses, that's when you put the -1 there. That's when you put the -1. Oh, that's not an exponent. Whenever you use the -1 in that position, it always means inverse. Now, for this guy, the domain would be -1 to 1, and the range would be -π/2 to π/2. So an inverse sine will only return angles between -π/2 and π/2. Now, what does the graph of the inverse sine look like? Well, the graph of the inverse sine is going to kind of be like that. When I flip it over the line y = x, it's going to have that sort of feel. You do not need to know what the graph of inverse sine looks like. You're never going to graph it, but just be aware that, oh, it's just this piece flipped over, so it's going to kind of have a different bend. Now, I know a lot of you like using arc functions. If somebody told you those were the same thing, they lied to you. They were probably trying to get your money and sell you real estate. Arc sine isn't even a function. Arc sine returns the infinitely many values. So when you ask the arc sine of, remember we said sine of π/6 = 1/2? Arc sine of 1/2 is π/6 plus k2 pi, comma 5π/6 plus k2 pi. It's every possible value. Arc returns every value. Inverse returns 1. And I'm amazed that people get this far and they didn't know that they're not the same thing. There's something you would actually have to change about it. Now, the only reason anybody ever used arc was because back in the olden days, before they had, good word processors and things like that, it was difficult typing that in. So there's a word that you need to see. I'm going to give you a simple example of something, because from a language standpoint, I want this to be absolutely clear to you. Back in pre-calc, you did something hopefully called the Mob's theorem. That was where you found all the roots of things. Sometimes they were, icky. So the Mob's theorem would be something like this. If I said, find the square roots, plural, of 1. Find the square roots of 1. You answered -1 or 1. If I said find the single square root of 1, you answered 1. What? Okay, that's just weird. If I said find the fourth roots of 1, then your answer would have been -1, 1, -I, or I. Why? Because each of those things, when raised to the 4th power, would produce 1. If I said find the 4th root of 1, you said 1. What's the difference? Because if I say find the single square root of 1, it's the same as asking for what's called the principal. Believe it or not, when you get to the higher levels of mathematics, every number has 2 square roots. Every number has 3 cube roots. Every number has 4 fourth roots. There's only 1 principal. So what we do as a default is when we say square root singular, we're actually saying find the principal square root of 1. But if I used plural and I say find the square roots of 1, then you'd know I mean both -1 and 1. I know that's confusing, but that's the language we've always used in math, and we will continue. So when you're saying find the arc sine, that doesn't return 1 value. If you said find the principal arc sine, now you're getting the inverse sine. If you're not using the word principal with arc sine, then arc sine does not return 1 value, it returns infinitely many. That's the difference. Now, most people don't make that distinction. You kind of have to. When you get to your upper level classes, if you used arc in an upper division math class, you're probably going to get it marked 100% wrong 100% of the time, because the math teacher is going to say, no. You have to know there's a difference at this point. You're not going to get credit for incorrect answers. Doesn't matter what your intent was. So just use inverse. It's easier notation and there's no ambiguity. But if I said principal arc sine, now principal arc sine that's too many syllables. There's actually another way of doing it, which I think is really, really funny. This is what I actually learned in college. If I want to say principal arc sine, and this is really funny, you capitalize the A. And I'm pretty sure most of you probably have never seen that. That's actually considered a universal way of saying principal, is you capitalize the arc. I find that to be kind of silly, but that's the universally accepted way if you don't want to write the word principal. Yeah, I just do that. It's easier. Okay, so with that understood, I can do the same thing for the cosine and for the tangent. In other words, I want to create inverse trig functions, right? So they can't use the entire number line. So if y equaled the cosine function, what would I have to restrict the domain to make it so that the inverse was a function? Well, it's useful then to know what a cosine graph looks like. Okay, we don't do graphing a lot in this class, but it's good to know that the cosine looks like this. So just like the sine, I want to go peak to peak. So I go here or here or here or here. Well, I really would like to include 0. That would be useful. So the most logical, the one we chose generally is that one. And that would mean that my domain is going to be 0 to pi. And my range is going to be -1 to 1, just like before. Then I can define the inverse cosine, and the inverse cosine will only return values from 0 to pi. Remember, you take the trig function of the angle, you return a ratio. Sine of pi over 6 is a half's a ratio. If I take the inverse trig, it's inverse trig of the ratio, and I'm returning an angle. You don't take an inverse trig of an angle. That has no meaning. Okay, you have to do it. You have to switch them. And then what about the tangent function? Well, the tangent function, as we know, has asymptotes, which are cool. So tangent, every pi units, there are asymptotes. So the tangent function forever and ever and ever and ever. Now, the one wonderful thing about the tangent function is that the range of the tangent function is all real numbers. You get the whole number line. When you enter something, a tangent of an angle, any real number is fair game. Okay, so the range in this case, oops, is -infinity to infinity. But what domain should I use? Well, just pick one of these. And we usually pick that one because it includes the origin. But the asymptotes, that's at -pi/2, that's at pi/2. So my domain, if I restrict it from -pi/2 to pi/2, almost the same as the sine. The sine is a closed interval because I can have endpoints. The tangent is not a closed interval because there's asymptotes. So if I restrict the tangent to this domain, then I have inverse tangent defined. Okay. Now, there's one more. You're never going to work with inverse cosecant. You're never going to work with inverse cotangent. It's just not going to happen. But you will occasionally work with inverse secant. You will occasionally work with that one. So we want to be able to define that one. Now, secant's a little bit tricky. So the way most of you probably learn to graph a secant function, because I can't do the inverse if I don't know what the function looks like, is you took a cosine wave. Okay, it's not very accurate. Okay, let's make the little. All right, I took a cosine wave. Secant is the reciprocal of cosine. Oh, so when the cosine is 0, secant would be undefined. That's where my asymptotes would be for the secant function, where the cosine is 0. Okay. When the cosine is 1, the secant is 1, because the secant is the reciprocal. When the cosine is -1, the secant would be -1 because it's the reciprocal. Okay, so I get this sort of thing here. So my cosine is positive, but getting smaller. So its reciprocal is positive and getting bigger. Here, same thing. And many of you'll say, oh yeah, I remember. That's how I learned to graph a secant function. You just start with the cosine function and then you just think reciprocals. But the secant has asymptotes. Now, here's the problem with the secant function. I can't give you one continuous interval because there's asymptotes. Well, so then do I just go from here to here? No, I need a portion of the secant graph that carves out everything. Now, the domain of the secant is not all real numbers. It's like the tangent, right? The domain of the secant is negative pi over 2 to pi over 2, then pi over 2 to 3 pi over 2, and so on. Because all the odd pi over 2s, are going to be vertical asymptotes. So, and the range of the secant is 1 to infinity, negative infinity to negative 1. It's two different intervals. So I need to be clever, and I need to pick out a portion of the secant that's 1 to 1 and carves out all values. So what I need to do is take half of this, either that piece or that piece, and I need to take half of one of these guys. But how do I know which ones to use? We'll go back to the cosine. Cosine is 0 to pi. Right now in my picture, that's, where are we? Sorry. That's my, I'm sorry, here we go. I'm like looking at the wrong spot. That's pi right there. Sorry. If I go 0 to pi for the secant, I would take this piece and this piece, and that makes perfect sense. I've then carved out every possible range value, right? I took half of that piece, and my interval was continuous except for that darn thing in the middle. So if y equals the secant function, and I restrict the domain as follows: 0 to pi over 2 open, union pi over 2 to pi closed. It's almost exactly the same as the cosine with one value removed, and then I will sweep out all possible values. That makes the secant probably the trickiest of the bunch. But then the range will then be negative infinity to negative 1, union 1 to infinity. Because if you look at the graph, that's what we have. Yikes. But that allows us to now have an inverse for each of them. Again, you're never going to run into inverse cotangent or inverse cosecant, so we're not even going to bother with those. Now, we're not even going to do the calculus till next day. Today, I want you to get familiar with how to answer questions involving inverse trig. So let me remind you of something you did in trig and in pre-calc. If I said, all right, sine of theta equals, keep it simple, equals 3/5 theta in the first quadrant. Find the remaining trig functions. Okay, this is a problem that you would have done in a remedial trig class, in a pre-calculus class, hopefully. Now, do I need a calculator to do this? Actually, no. Calculator won't help me in this case. So how to answer that question? I'm telling you the sine of theta is 3/5 and theta is in the first quadrant. So draw a picture. Draw a picture of a triangle. Now think SOHCAHTOA, right? Everybody knows SOHCAHTOA. Draw a picture where the sine of that angle is exactly 3/5. Well, if sine is opposite of hypotenuse, then this is the picture I would draw. The sine of this angle is clearly 3/5. I don't want a unit circle. No, I don't want fractions in roots. It's too icky. Now, with that said, what would this piece be? Well, let's see. Pythagorean Theorem, right? That's it, right? So 5 squared, 25, minus 3 squared, 9 would be 16. This would be square root of 16. Oh, okay. Therefore, cos theta, tan theta, secant theta, cotan theta, cosecant theta. What are they? Piece of cake. Cosine would be 4/5. Tangent would be 3/4. Secant would be 5/4. Cotangent would be 4/3. Cosecant would be 5/3. Okay, that was pretty darn easy. I think we all agree with that. Okay, that was not a difficult question. This is what you did way back when. The trick to doing this correctly is to draw the picture that coincides with that statement right there. So now I'm going to ask it in a different way. This is what we did in the lower level classes. So now let's take a problem. Now I want you to find the cosine of the inverse tangent of 2/3. What? Wait, how do I do that? The exact same way. We're going to draw a picture. Now, what picture am I supposed to draw? Well, that's not obvious yet. Now, first off, inverse tangent of 2/3 produces an angle, and then I want the cosine of that angle. Do I ever actually have to find that angle? No. Finding that angle would be utterly useless, worthless. It won't help me, and I'll do some hideous decimal and mess everything up. Nope. So think of this way. This statement here means that the tangent of theta, whatever theta is, the tangent of theta is 2/3. I'm asking you to find the inverse tangent of 2/3, which would produce an angle such that the tangent of theta is 2/3. Oh, how about I write it like this? If tangent of theta is 2/3, find cosine of theta. Isn't that the problem we just did? Except I'm only asking you for one trig function rather than the other 5. Again, this is my angle, and I'm asking for the cosine of that angle. So if tangent of theta is 2/3, find the cosine of theta. So let's draw a picture. If the tangent of theta is 2/3, then that would be 2 and 3. Okay, what would the hypotenuse be? Well, 3 squared plus 2 squared, that'd be 9 plus 4 is 13. So this would be root 13. So what is the cosine of theta? 3 over root 13. So the answer here is 3 over root 13. Could I do this on a calculator? Sure. Yeah. Any calculator, you enter cosine of inverse tan of 2/3, but you're not going to get this. You're going to get some decimal approximation of that. Oh, but I want that. Yeah, that's a better answer. And this was way, way easier. Now, we can do this for anything. There isn't a problem that we can't do this for. So let's do another one. All right. So we're reviewing. This is like remedial trig stuff. Why are we reviewing this? Oh, you'll see. All right, let's do the sine of, how about the inverse cosine of, let's say, -1/4. Now, in the previous example, quadrant did matter, by the way. Quadrant absolutely did matter. Now, remember, cosine. Where's the cosine restricted to? We said 0 to pi. Another way of saying that is first and second quadrants. Oh, so this is my theta, but the inverse cosine of a negative number therefore must return a second quadrant angle. Okay, that's really important. In the previous example, I asked for the inverse tan of 2/3. 2/3 being a positive number meant it was in the first quadrant because the tangent returns first and fourth. So the fact is that each of the inverse trig functions will return angles in 2 different quadrants. That's how you determine the positive and the negative. So again, the cosine of theta is equal to negative. So therefore, theta is in the second quadrant. How do I know? Because we restricted the domain of the cosine to be between 0 and pi. So that restricts the range of the inverse cosine to only return angles in the first and second, between 0 and pi. Okay. Now, why is this important? Because that's the picture I would get. See, that's the picture I get because it was a first quadrant angle. Okay, this is important. So if the cosine is -1/4, so ka toa, that means the hypotenuse is 4. A hypotenuse isn't going to be the negative. Think coordinates. Oh, -1 in the x direction. So that coordinate is -1 comma something. So I can think of this as being 1, but it's -1 in the x direction. So what goes here? 4 squared minus 1 squared is 15. So this would be root 15. Okay. Now I want the sine of that. But in the second quadrant, the sine is positive. So my answer is root 15 over 4. Beautiful. The second quadrant angle, but I took the sine of it. And the sine in the second quadrant, I know, is positive. So that gave me a perfect answer. nice stuff. You say, well, this again, why are we reviewing this? This is so simple. You're right. I can do this on my calculator. Well, yeah, I'm going to get decimal approximations on my calculator, but that's okay. All right, so let's keep going. We're going to get good at this, whether we want to or not. I want to do the tangent of, how about the inverse sine of, how about 3/5 x. Yeah, I'm throwing a variable in there. Is that legal? From this day forward, you're only going to see variables. You're never going to see constants ever again. I looked ahead. Yeah, you're never going to be asked to do this with numbers. You're going to be asked to do this only with functions. So how do I do this with a function? Same way we did it with numbers. Draw the picture. If this is my theta, doesn't that mean that the sine of theta is 3/5 x? So I need to draw a picture. And by the way, the default will always be just draw it in the first quadrant, and I'll show you it won't change anything. How do I draw a picture where the sine is 3/5 x? Think of this now as a quotient. In other words, think of this as 3x over 5. Oh, if I think of that as 3x over 5, then there's my 3x, and there's my 5. Now, the sine of theta is 3/5 x. It's 3x over 5. Then what would that make this side? Well, make it that squared minus that squared. So 25 minus the square of 3x, or 9x squared. That cannot be simplified. So what is my answer? Well, the tangent would be this over this. All right, and there's my answer. That's it. Oh, well, that wasn't that bad. That was the same thing we did with numbers. Now, there is one little catch here. I drew a first quadrant angle. What if x were a negative value? If x were a negative value, inverse sine of a negative value would return a fourth quadrant angle. Because remember, we've restricted the sine to first and fourth. Negative pi over 2 to pi over 2 means you're in the first and fourth. That's my arm being, sweeping at it. So what if x were a negative value? Then shouldn't that be a fourth quadrant angle? And then the tangent of a fourth quadrant angle would actually be negative. If x were a negative value, you're right, I would be in the fourth quadrant. And the tangent of that value would be negative. So if x were a negative value, this is negative. In other words, I do get the same answer. If x is positive, it's a first quadrant angle, and that ratio is positive. If x is negative, then it's a fourth quadrant angle, and that ratio would be negative because I'd have a negative on top. So the default is, when you're doing this with variables, always draw a first quadrant picture. The signs will always take care of themselves. It's kind of nice. You don't have to worry about it. So let's try another. Let's say I want the, let's do the cosine of the inverse tangent of, how about, I don't know, 3 over x. That looks kind of creepy. It doesn't matter what I write here. I'm just going to do that picture every time. All right. So like before, tangent of theta is 3 over x, and I want you to find the cosine of theta. So if the tangent is 3 over x, well, that's perfect. That's a ratio. I want my trig functions to look like ratios. Then they look like SOHCAHTOA. TOA. So if that's TOA, then that's clearly 3. That's clearly x. Oh, okay. It actually is that simple most of the time. So what goes here? X squared plus 3 squared under the root. The question was, what is the cosine of that theta? And that would be this over this. Okay. Let's do one more. This one you guys are going to do. Let's do the cosine of the inverse sine of, how about 3/7 x squared. Just keep kind of crazy. All right. I'd like everybody to do this on their own. So again, in this case, when I rewrite this, this is critical that I represent this as a ratio. See, the thing is, if I represent it in this form, then I'm going to put this here, and then I'm going to put a 1 here, and then I'm going to have something ugly here that's really hard to work with. You don't want to do that. You don't want any fractions and things like that in your roots. It gets way too messy. So always represent this as a ratio, then simple SOHCAHTOA, boom, boom. It wouldn't matter what I put here. No matter how complicated this is, this process should be very clean and relatively simple. All right, so let's do the usual now. We're going to take a break.